Right. Hello, everyone. This is Mr. Younger again. We're here for week seven. Double checking that. Week seven, February 25th to March 3rd. This is Tuesday of that week, and this is the day where we discuss what we're doing for lab. This week, I actually sort of have two labs that I'm going to fit in. One is a more traditional lab where you're going to have data to analyze and a report to write or fill in, that sort of thing. But the other one is one where I'm trying to teach you a more rigorous way to treat numbers and uncertainties and measurements. Any person that actually takes a course or takes a degree in a experimental science, especially ones that require mathematics of any sort, will ultimately need some kind of error analysis type course. And most bachelor's degrees require such courses, but not all of them have them. Some of them they just sort of have a lab course, and then they sort of on the side teach you some of the problems associated with errors and uncertainties and propagation of error and stuff like that. So this other lab is our attempt at TCC to teach you specifically how to treat error analysis, errors, uncertainties, and stuff like that, as opposed to the more traditional, but admittedly not useful, not reliable sig fig method. So yes, in our labs throughout the semester, unless I explicitly tell you otherwise, we will be continuing to use significant digits. But there is almost always one or two labs where I'm going to have you implement some of the more rigorous processes that we have in error analysis. So we're going to discuss that as well. So let me go ahead and get started by sharing my computer screen with you so that you can see the labs we've got planned for today. So you're now looking at week seven, and you'll see sequence one, lab six, linear graphing two, 2019. You can ignore the year. Basically, we usually update it, and I don't necessarily change the date on it, which I should. But I have a master file where I keep the newest dated ones. We also have in that area a file that says Lab 6 Linear Graphing 2 Addendum. So that's the addendum that you use to convert this lab, which is what you're actually doing, to a lab that you can do at home. So this lab actually has quite a bit of stuff that we would normally want to run experiments with equipment that would be nice to have, but we don't always have access to that equipment if we're doing an online lab, and that's what we're doing here. So let me start by talking about the linear graphing 2 lab, so you'll have an idea what that is. I'm going to go ahead and click on it so we can see it. I want to remind you guys that you need to download this to actually start filling it in. You don't want to try to fill it in while it's up here. Not only that, my rule, remember, is you're going to take this Word document, download it, and you can type in data and stuff like that. But anywhere you actually type in data, I want to make sure you do not do that in black font. You want to make sure it's in a colored font where I can easily see what data you've entered, what equations, what anything you've entered into the document versus what was in the original document. So that's a really big part, and you're always going to lose points if you fail to do that. Now, if you put in handwritten parts, or if you actually take photographs of handwritten parts or even photographs of typed parts, it's pretty obvious that they did not come in the original document. So you don't have to worry about that. So feel free to include handwritten notes or include photographs of handwritten calculations or handwritten uh, derivations, stuff like that. So, anyways, here's the linear graphing. It tells you what we'd normally need if we were, again, face-to-face meeting in a lab where we have a picket fence and a force probe and string and wood and blocks and stuff like that. I, of course, invite you all to come by any one of my labs, and we'll show you this equipment and let you even use it if you wanted to. We're not trying to prevent people from getting experience in the lab. In fact, we'd prefer it, but we're trying to offer an opportunity for you to get the lab in a way that doesn't necessarily completely keep you from maintaining your job and all that good stuff. So you look here, it says introduction. Graphing a linear relationship can be useful in finding constants. For example, when we graph distance versus time, the slope of the line was the velocity, and the equation d equals vt plus d0, where d0 is the y-intercept. So you can see how we normally do this. We can plot something on the vertical axis. Remember, the vertical axis is where you plot the dependent variable, and the horizontal axis is where you plot the independent variable. And in this case, they're showing a graph of force in newtons versus acceleration in meters per second per second. Notice my wording too. Force versus acceleration means y versus x. So when you say it or when I type it, you should interpret it that way. If a relationship is linear, then we can find the slope and intercept, and the slope and intercept may be constants of interest or may be used to find other constants. So that's the main part we're trying to teach you here is yes, we should be able to find relationships and prove whether relationships actually match what our theoretical physics ideas comes up with, and we should be able to do that going forward when we're dealing with variables that we haven't encountered before and equations we haven't worked with before. So this lab is a continuance of trying to make data look linear when it's not necessarily going to be linear. So for instance, you know that x equals 1 half at squared plus v0t plus x0. That's clearly a quadratic equation. So if you were to plot x on one axis and t on the other, usually x on the vertical axis and t on the horizontal axis, you would know that would make a parabola, and therefore a linear curve fit would be goofy looking and wrong. So don't do that. But sometimes you can accidentally not realize it because you're just looking at a small part of the curve and it looks pretty straight. So you got to pay some attention to that when you actually plot your data, and plot your data as big as possible so that you can tell whether it really is a straight line, or if you've got, clearly you've got three data points on one side and they're in the middle of a string of data, and then you got two data points on the other side beyond the data, and two data points on the other side before the data. Then there's a good indicator that that might actually not be a straight line. So for instance, if you had a straight line like this and you had data point, and then like three on this side and then a couple more on that side, that might actually be a curve, even though it sort of fits a linear graph. So you got to keep those things in mind. But the big thing we're talking about here is we're going to use specific data to, for instance, determine the density of aluminum. In this case, we're going to actually, in principle, you guys would be measuring spheres or rectangular blocks or cylinders made out of aluminum, and you'd be measuring them with a vernier caliper so that you could get very precise data. Get instead of two decimal places, which is the norm for a meter stick, or any centimeter scale that has 10 increments between 1 centimeter and 2 centimeters, 10 spaces. Any of them that has that, you're supposed to be able to get two decimal places unless some extraneous measurement problems make it impossible to get that one. Then you have to estimate the instrumental uncertainty. But in this case, we're going to be using vernier calipers, or we would have been using vernier calipers, and they give us three sig figs. Or I should say three decimal places. It could be, four sig figs or five sig figs, depending. Obviously, if you have a vernier caliper, it's very rare that it's, 12, 14, 15 centimeters long. It's usually on the order of maybe 9 or 10 centimeters, in which case you could get two sig figs to the left of the decimal and then three after. But other than that, it's almost it's almost always just four sig figs total. So, anyways, we are going to measure volumes and we are going to measure masses. We will give you that data. That's how we're going to transform this into an online lab. And then you're going to plot very specifically. You could plot, for instance, the volume on the vertical axis and the mass on the horizontal axis. If you did that, then the slope would be cubic centimeters per gram. That's not very helpful because the density is in grams per cubic centimeter. So you might prefer instead to plot the mass on the vertical axis and the volume on the horizontal axis so that the slope would then be, or at least the units of the slope would then be grams per cubic centimeter. And if you actually come up with a straight line, then that would be a good indicator that that slope is a good measure of the density. The big thing to realize with that is it being a straight line tells you that your model, which in this case was basically mass equals density times volume plus zero, that's a y equals mx plus b type equation. So this is actually helping you that way by seeing it, but it's just another way of getting the actual density of aluminum. The big point, though, is that by doing this with separate objects and then taking a graph of them, in some sense, you're finding the results of all the measurements as opposed to just focusing on one, which could be riddled with error. So that's an advantage as well of making plots, and that's why I repeatedly tell you guys when you actually make the data, you put the data on the graph, and then you find a line of best fit. Especially in the linear cases, you find a straight line of best fit. Once you have that line of best fit, you completely ignore the data points from there on out. If one happens to lie exactly on the equation that you determined to be the equation of best fit, then yeah, you can use it. It's not like you're forbidden to use the data. It just happens to be that that particular one was completely consistent with what you deemed the result of the experiment, which was the linear line. So keep that in mind. Once you've made the line of best fit, you're not supposed to go back to the individual data unless you happen to luck out and find that one of the data points lies exactly on the line of best fit. What we normally do, for instance, if you were doing a hand fit line of best fit, is we would look for 2 points on the line of best fit where the crosshairs of the graph paper hit. Because in that case, that's either a whole integer or a half integer or a quarter integer or a tenth of an integer, and the same thing with that line. So you have very specific, well-known points. So it's often very smart to choose two of those points where it hits right through the intersection of two lines of the graph paper. That's one point, and then do another place where it hits two lines intersecting on the graph paper, and that gives you 2 points. That's enough to determine the slope. You can then, of course, plug one in as y and x for y equals mx plus b, but now you have m, so you can use it to solve for b. As always in my class, when it says print graph, what I mean for you to do is to capture a screenshot of the graph and then insert the graph where it specifically asks you to make the graph or where it specifically asks you to print the graph. Okay, so you don't actually have to physically print out anything. We're trying to, not necessarily just randomly waste paper. So you would just want to take a screenshot of it, and I always will not take off points if you show me more graphs than are requested. However, if they ask for a graph and you don't put it, I will take off points. But if you weren't asked for a graph and a graph was critical for your understanding, even though they didn't tell you to print it, I would prefer to have that there. I'm not sure, depending on how the wording of the lab would be, I'm not sure I would take off points for you not having that graph. But if it was pretty obvious that the graph was really necessary, I really want you to consider putting the graph in, and always make the graph big enough where I can read the any kind of text that's written on it. For instance, the curve fit, if that's on there, you need to make that curve fit big enough, or you need to make the picture big enough where I can read it. And I'm never going to be offended if you also give me a separate photo of the data. I wouldn't mind one big photo that had the data and the graph, but the problem with that is it often makes the graph so small that I can't then read units and increments on the graph, nor can I read the equation of best fit and that sort of thing. So the main thing is make sure that you could imagine an old person with really bad eyesight reading your lab report, and if you find that that really old person with bad eyesight might not be able to read it, then you probably need to make it a little bigger for Mr. Younger. Okay. All right, now that we're finished with that part, we'll go on. There is a part where you're actually going to study kinetic friction, and in that case, you would be pulling. Of course, we're going to give you the data, but you would be using a force probe that measures in newtons and reports it to a lab pro that puts it up on a screen of a computer. In our case, we'd be using, Pentium type computers or whatever. But either way, it actually shows in real time how much force is being supplied by the force probe, and they would ask you to drag this block of wood with a certain amount of weight on it over some distance at a constant speed, because that can give you a measure of how how much friction force there is, because if you're moving at a constant speed, i.e. not accelerating, then the net force on the object is zero. So that means the friction force, which is maybe this way, and the pulling force, which is that way, they have to actually be equal in magnitude but opposite in direction in order for you to have a constant velocity. So that's why you can make the assumption that whatever forces the force probe is reading as you pull the block at constant velocity, that force is exactly the force that the friction force is. Okay. So you're going to do that, and it specifically when we do the lab in person, you would increment it by another 200 grams each time. So the first one is a wooden block with a 200 grams of mass on it, and the total mass therefore is the mass of the wooden block plus the 200 grams. And then the next trial, where you're actually going to do 3 trials for each, just to make sure you get a good estimate of what the friction force is. Then you're going to add another 200 grams, do 3 more trials, take the average of that. That gives you the average kinetic friction for that particular mass and for the previous particular mass. And you keep doing that until you fill up the data table. And then you can make a plot. As you can see here, they're asking you graph the average kinetic friction force on the y-axis. So the friction force is on the y-axis, and the normal force on the x-axis. So the normal force is the basically, because this is going to be a level surface, you know from your lecture that you normally take the summation of forces in the y direction is equal to mass times acceleration. But if you're imagining the y-axis pointing up and down and the x-axis pointing left and right, and the surface is level, then as you're pulling at a constant velocity, you do not expect this y-coordinate to change. And since it's not changing, that means the y is a constant. And of course, to get the y velocity, you take the derivative of y with respect to t, but the derivative of y with respect to t when y is a constant is 0. So that means the velocity is 0, and then you take the derivative again, the velocity is still 0, and you take the derivative again, the velocity is still 0. When you have a velocity that's 0 and continues to be 0, then that means the acceleration is 0. So at the end of all that, we can conclude that the normal force must in fact be equal to the weight. So if you take the mass of the block of wood plus all the mass of the masses sitting on top of it in each instance, and you multiply it by 9.8, that's the weight of the block plus all the stuff you're pulling. That weight is exactly equal to the normal force. So you can make a plot, as I said, of the average kinetic friction on the vertical axis versus the normal force on the horizontal axis. We know that the friction force, at least kinetic friction, is supposed to be the mu static times the normal force. So you're making the assumption that F average is equal to mu times the normal force. That fits perfectly with y equals mx plus b, because the x plays the role of the normal force, the y plays the role of the average kinetic friction, and the b should be 0. But that means that the slope in y equals mx plus b is going to be your coefficient of kinetic friction. So that's really what you're shooting for there. It says print a copy of the graph with included trend line data. Again, that just means take a screenshot of it. You can go on to determine the acceleration of gravity. In this case, where we actually took a mass, it was a little cart that we set on a air track, and the air track more or less creates a very close to frictionless surface. But in this case, we can actually figure out exactly what the friction is. So we have a inclined plane that really is a linear air track, and the linear air track's like almost 2 meters long, and the spot from one leg to another is 1 meter exactly. And what we're going to do is we first level out the linear air track, so that if you put an object, dead center on the linear air track, specifically between the legs, because there is in principle a little bit of sagging of the linear air track, probably not measurable, but anyways, there is possibly a little bit of sagging between the two legs of the air track. So if you put it dead center, that should allow that sagging to help the object stay where it is. And then you set it there. And what you want to look for is that when the air track is on and the cart is sitting on the air track roughly in the center, it shouldn't make any rapid moves to move to the right and speed up, speed up, speed up, or to the left and speed up, speed up, speed up. And the way you're going to do that is you're going to make sure you adjust the little legs or stubs on the bottom of the legs to make sure that it's fairly level. You can also just, use a type bubble level or something like that to level it out first. That would be fine as well. But the big thing is if you can lay that cart on there and it doesn't move and then speed up and then move and speed up and move and speed up to one way, then you can be pretty assured that it's fairly close to level. Now that you've got it leveled, what you want to do is then prop up one of the legs so that you can make it an inclined plane, and you're going to prop it up in principle again because we're doing this sort of virtually. You're going to prop it up with little 100-gram masses, and they have a pretty much fixed thickness. But the nature of it is that that fixed thickness will be the height of one leg and how much it's higher than the other, and then the distance between them is the actual hypotenuse of a triangle. So you've got a little height right here that is the height of one or two or three total 100-gram masses, and then you have the hypotenuse that's at an angle that's the 1 meters between the leg. So if you consider sine of theta as opposite over hypotenuse, then you realize that the sine of theta is actually the height of however many blocks you have, whatever that total height is, divided by 1 meter. If you're measuring the height in meters, then you've got some number of meters divided by some number of meters, and you have a pure number. That pure number, in fact, is the sine of theta. So you can actually plot on the horizontal axis the sine of theta just by plotting the height in each instant. So that's a key thing to understand. Now, the equation that we're looking at is Newton's second law, F equals ma, and remember the F means the sum of all the forces. You've seen in class that when we deal with inclined planes at an angle theta, then the gravity force parallel to the inclined plane is is mg sine theta. So that's what they're showing here, mg sine theta minus a friction force that would also be parallel to the surface but would be in the opposite direction of gravity. So they're calling it mg sine theta minus F, and that F is supposed to represent the friction force. Specifically, in this case, it'd be kinetic friction. All of that, according to Newton's second law, is equal to the mass divided by, or excuse me, times the acceleration. That mass is the mass of the cart in each instance. So you're actually going to have a mass that changes from one case to the next if you did it like we did up here, where you kept adding another block or adding another 100, 200-gram masses or whatever. In this case, you'll see what the data is. But the neat thing is, if you decide to instead divide this entire equation by capital M, then you'll get A, which would be could be on the vertical axis, because when you divide MA by M, you just get A. And if you divide this side by M, you get G sine theta minus F over M. The G will be the slope. The sine theta, which I already told you was really the height, will be the X value, and the intercept will be F over M, the friction force divided by the mass. So if you actually figure out what the y-intercept is, and you take that and multiply it by the mass of the cart, that will give you the actual friction force. And the slope should give you the actual value of G, which is supposed to be 9.8. So that's how that's all supposed to work. And they ask you specifically, when A is plotted against H, what will be the slope, what will be the y-intercept. I think I've explained that pretty well, but you need to internalize it in such a way that you understand it, or you're just going to repeat my answer. And my answer's fine. It's just more a fact of I need to make sure you guys sort of can get that and understand it. So, replay this part of the video if you need to, or look at the other video that I've posted for this particular lab. Here's where they show the procedure. You can see in this case, we have a cart on a linear air track. We have this flag device basically right here, a picket fence or whatever you want to call it. And basically, the system that we work with knows exactly how far apart the black lines are on this ladder, and it goes through a photo gate, and the photo gate says, I can see light, I can see light, I can see light, oops, I can't see light. And then I can see light, I can see light, I can see light, and then oops, I can't see light. And it knows exactly how long those clear strips and black strips were. And from that, it can calculate the acceleration immediately. In your case, you're going to have the acceleration data, and you're going to have the H data for each of them and the mass data, and you can analyze all that as I spelled out. So you're just going to follow this principle, and you can see you'll get an equation for the line. It did say print a copy of the graph, so yes, you definitely want to include, obviously not a printed copy of the graph, but you do want to make sure you insert a photo or a screenshot of the graph big enough so that I can see it, and include the data, which luckily is right there, so it shouldn't be a problem. Just remember, if you type in data into this table, which is certainly fine, just make sure you do it in a font other than black. That's the whole lab. It's really not that bad, and that's why I chose this lab to be the lab that we do two labs on. So now that you know that, let me show you, going back to the module, exactly what the addendum tells us, because the addendum is what makes this lab into something that can be done at home. So we open up the addendum and we wait for the interwebs. Okay, so it says linear graphing 2 addendum. View the video to see how the data was gathered. That's really a good part. That's the other video that I shared with you guys. There's a password, if I remember correctly, in the actual title for the video, so you got to make sure you copy that down first and then click it. Uh, to get to the actual video. It says view the video of the to see how the lab data was gathered. Complete the lab as instructed in the lab book, but use the data below instead. So for the density part, that's when we were measuring the aluminum objects. One of them was a cylinder, and the cylinder had a mass of 61.32 grams. It had a diameter of 1.92 centimeters, and it had a height or length of 7.64 centimeters. And then we did three rectangular blocks. We didn't do any spheres. Remember the formula for the volume. First, we're all doing volume in cubic centimeters, and we're doing mass in grams, but the formula for the volume is pi r squared times length, since we call it length here. So you need to actually take the diameter and either divide that by 2 so that you have the radius, and then you could use pi r squared L. But if you're going to use a diameter, then you just have to make sure you allow for that, because the diameter is twice the radius. So in that case, you'd have to say d squared L over 4. So if you want to use a diameter, that's acceptable as well. But by using it in centimeters, it'll automatically come out in centimeters cubed. You've got the mass there, so you can plot the volume on the horizontal axis and the mass on the vertical axis. Similarly, you have three blocks, each of which are rectangular. It doesn't matter really which one's called the length, which one's called the width, which one's called the height, because length times width times height is the same thing as width times length times height is the same thing as height times length times width. So in all those cases, you're fine. There's the masses as well, so you can make a plot of all those. In the kinetic friction case, here's your three trials. You're going to have to take the average of these three trials to make the plot, the data point for the plot, and this is the mass that we use in each case. Technically, I think it's acceptable for you to assume that these masses were 0.400. I don't know why I wrote them in as if they're all 1 sig fig. Uh, I don't really think that's good at all. Uh, But what I would do, actually, these bottom two, of course, are 2 sig figs. But what I would do is assume all of them have 3 sig figs. That'd probably be best. Just assume these masses all have 3 sig figs. I can't imagine we actually didn't do it to that level of precision, but for some reason we recorded it that way. And then finally, in the last part, you can see here's the height. Remember, that's what you're going to plot on the horizontal axis. And it turns out to be exactly equal to, since the hypotenuse was 1 meter, the height is also measured in meters. Therefore, the sine of theta is the height divided by 1.00. Therefore, the height is actually the sine of theta, so that the slope should be g and the intercept should be f over m. I think that's the right one. Yeah. So, anyways, the mass of the glider with the picket fence is 286.3 grams. So you do need that as well. So that's the addendum. That's all we have to do to get that part correct. Now I'm going to go over the other part of the lab, and this was really pretty straightforward. There's a little bit of calculus that you get to use, uh, but other than that, it's really not that difficult. To deal with. It's just teaching you some statistics, teaching you a little bit of multivariable calculus, that sort of thing. But I try not to. Uh, I'm not trying to completely reteach the course for you so that you have the equivalent of a error analysis course. I'm just trying to give you enough of an introduction where you would know how to properly run a lab or do a lab in a real life experiment. So what that one is error propagation. This is where you'll turn in the error propagation. You can see I pushed the date back to March 11th. Linear graphing 2 will go here. If you need to refresh yourself on the procedure for making a lab and that sort of thing, then go back and look at like the first lab or the second or the third. I put all that full discussion in that one. I didn't put it in linear graphing 2 yet. Probably will, but like I said, you can look back at linear graphing 1 or one of the previous labs, and it has a full description of what your lab report is supposed to be. The error propagation. This is a video to showing you that. That's another video of explaining that. That's another video of explaining that. This is the video I talked about of showing you specifically the experiment being run. There's also a part here where I'm going to have a file, which I just had to update it, so I haven't put it up here yet. So I'm going to actually take this file, which is error propagation 1.4, and I'm going to put that in there. That's the actual document that you're going to fill in with right answers and photographs and stuff like that and turn in right here. So let me read that to you real quickly. Not really read it. It's a lot of wording, but it's definitely something you should read. Again, waiting for the internets. Well, it's 12:35. This is normally the time where people are supposed to be logging in if they have questions, because this is also an office hour, but I haven't seen anybody try to log in yet. Still waiting for the internet to upload my document. If it takes too long, I can always just open it up in Word and then show you the Word screen, but this should come up any minute now. I don't know why it's taking so long. I'll go ahead and start explaining what it's going to say anyways. So it turns out that using significant figures to work in a lab gives you some, fairly reasonable arguments and fairly reasonable logic in concluding how many decimal places a number should be rounded to and stuff like that. But you can look on my YouTube channel and you'll find videos specifically where I show you cases where sig fig rules actually give you completely horrible results. So you can check those out if you want to get a feel for exactly what is a bad result and exactly how did sig figs deal with it versus how did the error propagation stuff deal with it. It does look like this is going way too slow, so I'm going to open the document in Word, and now I'm going to share a different window. So let me stop sharing this real quick. Now let me share the other window, which I think is, yeah, that's it. All right, so we'll share this window. So this is error propagation part one. There's no part two yet. I mean, there is actually, but I'm not necessarily going to make you guys do that. So what it says, using sig figs in labs is not really good, very good or reliable. In fact, there are whole courses taught on just dealing with measurement uncertainty and how those uncertainties affect the outcomes of calculations. Such courses are often taught using John R. Taylor's An Introduction to Error Analysis. the study of uncertainties in physical measurement, and I even gave you a link to a uh, a cheap version that you could get from Amazon if you so desired. Don't need it, but if you are curious and you know that you're considering majoring in a physical science that entails experiment, meaning you are going to be an active experimenter or you are going to be reading actual experimental papers, then you definitely need to know this stuff at some point. And now might be a good time for you to invest in a copy of that book. It's not up. I mean, it's not required, obviously, but it's just there. So, any student completing a degree in experimental physics or astronomy, cosmology, chemistry, or a related engineering field in which experiment is important should have such a course or be prepared to teach it to themselves. So that's a lot of times that's exactly how it happens in science and engineering. Is a lot of stuff you just have to teach yourself. I wasn't, for instance, fortunate enough when I was at East Carolina to have a course in, well, actually, I ultimately did, but initially I was unable to have a course in differential geometry. There was no option for me to take a course in tensor calculus or calculus on manifolds, but I was wanting to major in specifically general relativity, and therefore we basically find various textbooks on those subjects: differential calculus, calculus on manifolds, topology, uh, Lie algebras, group theory, all that sort of stuff that we needed, and you just had to teach yourself it. So that's not uncommon within the education system, especially at the university and college level. A lot of stuff you just have to teach yourself. So I just gave you that. Any student, like I said, should have such a course or be prepared to teach themselves. The relevant analysis requires multivariable calculus and a good deal of statistics, so we'll not tell you from where all the rules come. Instead, in some cases, we'll just give you the formulas to be applied and rules to use. So some of it I sort of motivate it so it makes sense. Like there's something that looks just like a Pythagorean theorem, but it's in, any dimensional. So it could be literally, 400 dimensions. But there's a good reason to believe that a Pythagorean theorem exists for even that many dimensions, and therefore we use it. So that's just one example. Uh, the relevant analysis, like I said, does require those higher amounts of or higher bits of mathematics. But the big thing here is we need to consider a special case so you can get an understanding of exactly what the error propagation and error analysis entails. So we consider by just taking a measurement of a length of rod using a meter stick. Now, a meter stick, remember, is one of those things where if you look at it closely, you'll realize that it's measuring from 0 to 100. Ideally, the 0 and the 100 are a certain distance away from the end of the meter stick, or the end of the meter stick, at least at the 0 end, has a very hard or some kind of end that's not easily messed up, and then the 0 is right on that. I particularly prefer to have the 0 marking a little bit away from the edge so that we can always measure to the 0 mark, no matter how, or well, within reason, no matter how much the end of the meter stick gets mangled. But the main thing is you have a 0 and you have 100 is the largest measurement. That's why it's called a meter stick, because 100 centimeters is 1 meter. So it's measured obviously in increments of centimeters. But if you look, for instance, between 1 centimeter and the 2 centimeter mark, you'll see that there's actually 10 spaces. It goes one, you'll have the number one, and then there's a long line next to the one. That long line, sort of, you can treat it as if the center or the left edge or the right edge. I always treat it as if it's the left edge, but you can treat it as if the left edge of that long line closest to the number one is where the one begins. And then there's a space and a short line. That's one space. There's another space in a short line, another space in a short line, another space in a short line, and then you get to the fifth space, and then there's a long line. That long line corresponds to 1.5, and again, I would call the left edge of that long line 1.5, and then there's another space and a short line, 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 and then finally a tenth space and a long line, and the number two is next to it. Because those 10 spaces are there, that means that each of those spaces accounts for 1/10 of a centimeter, which is the definition of a millimeter. So you can read, for instance, if a measurement goes just barely past the first space and the first short line after the one, you can read that as 1.1 centimeters. But you should be able to read that better because you can certainly tell the difference between 1.11 centimeters and 1.19 centimeters. In other words, if it was really close to that short mark, one space to the right of the long one line, if it's really close, you'd expect that to be more like 1.11 or 1.12. But if it's really close to the next one, then you'd expect it to be more like 1.18 or 1.19. So if you look at that, then you should clearly be able to tell the difference between 1.11 and 1.19. What I would argue is if you're really looking at it rationally and taking your time, uh, you could definitely tell the difference in most cases, unless there's some problem with the actual thing you're measuring. Maybe the edge isn't completely straight. Maybe it's got a crinkly shape like that, or maybe it's in an awkward position, so you can't measure it that well. But barring all that, you should be able to tell the difference between, say, at best, 1.1 and, or say, 1.11 and 1.13. So I don't think you can tell the difference between 1.11 and 1.12, but I definitely think you should be able to tell the difference between 1.11 and 1.13. If that's the case, then your uncertainty is from 1.11 to 1.13. So they call it plus or minus what number gives you the difference between 1.11 and 1.13. That difference is 0.02, and you want it plus or minus, so you have to cut that in half. So the difference is you're going to call that uncertainty plus or minus 1 point, or excuse me, plus or minus 0.01. So that's what a meter stick and anything else with 10 spaces between the 0 and 1. So if you look here like that, those little guys don't have the 10 spaces. They actually just have half, so that wouldn't work. But if you look at a regular centimeter scale, it would normally have, like I said, between the 1 and the 2, it would be uh, a long line for the 1, a space, 1.1, 1.2, 1.3, 1.4, long line, not quite as long as the first long one, but longer than the short ones. That's 1.5, 1.6, 1.7, 1.8, 1.9, 2.0. Okay, so they, by necessity, objects with that type of measuring marks written out on it should have an uncertainty of 0.01 centimeters. Any kind of digital device, you can just assume it's going to have an uncertainty of one in the last digit that it gives you, unless the manual tells you specifically otherwise. Okay. But either way, you now have an idea of exactly what we mean when we're talking about taking a measurement and that sort of thing. In the paragraph, I explain why we make multiple measurements. There's multiple reasons for that. And then I address specifically what is, if you do take multiple measurements, what is the measurement that you should think should represent the length, say, of the rod. And it turns out that should be, if you have access to individual measurements, and each one has a different amount of error in each measurement, then the weighted average is the gold standard. But we were not going to be doing any of that weighted average stuff in any of our labs this whole semester, other than, that's what we use to calculate your grade. But anyways, we're not going to have weighted averages to use. So in general, what you use, if you don't have a different measurement uncertainty for each trial, you're just going to take the average of them. Okay. You can, in principle, if you find out that you're, maybe you took 25 trials. If you did take 25 trials and you found that one of those data points was 3 standard deviations from the mean, we'll get to what standard deviation means later. But if you find that one of those data points is actually more than 3 standard deviations away from the mean that you got, you are experimentally justified in throwing out that data point, but only when it's 3 or more standard deviations away. Okay. And even, there is a little bit of possibility that it could be right in 3 standard deviations, or really more than 3 standard deviations is the standard by which you throw it out. All right. So now that we have that idea of taking multiple measurements and then taking a mean to represent the best possible measurement of that quantity, then you want to know things like, well, where do we round numbers to? And what if I use that number to actually calculate, let's say, the volume? Like earlier, I was telling you in that previous lab, we're going to measure the length, the width, and the height of a rectangular solid. Well, each of those lengths, widths, and heights have a uncertainty in it. Uh, what is that uncertainty? Is it just the 0.01 because we used a meter stick, or is it just the 0.001 since we used a vernier caliper? And what about when I multiply length times width times height? When length has one error, width has another error, and height has another error, where do I round that answer to? That's what propagation of error is about. And this tells you all that. So to start it all off, we have to tell you something about the standard deviation. So it turns out, statistically speaking, work has been done in the field of statistics, and we've reached the conclusion that if basically if you're making measurements and the measurements have random error, then it turns out if you use the appropriate formula for standard deviation, then if you did say a million trials and of measurements, one type of measurement like the length, say, then, if you actually computed the mean, that's your best estimate of the value, say, for one of those links. And then if you calculated the standard deviation, again, we'll get to the formula for that later. But if you did calculate that standard deviation, then you can take that standard deviation and add it to the mean, and that'll give you a big number that's bigger than the mean. And then you can take that standard deviation and subtract it from the mean, and that'll give you a small number that's smaller than the mean. And in fact, those two numbers, the standard deviation plus the mean and the standard deviation minus the mean, act as a interval of numbers uh, where there's a whole range of values, basically. What statistics has taught us is that the variable or if the measurements really truly have random error in them, then 681,000 of those million trials will fall within one standard deviation of that mean, because it turns out that 68.1% of the data is within one standard deviation, 95.4% is within two standard deviations, and 99.8% is within three standard deviations. Now, that's good. That's a neat thing to know. But really, when you're going to report experimental results, uh, you want not to say, hey, what would any other goober making this measurement get? No, you'd like to say, hey, if I had a million labs doing the same experiment that I'm doing, what would be their best value? What would be their mean for the length L? That's a better measure. So instead of using standard deviation, we use something called the standard error, which is actually also called the standard deviation of the mean. Hopefully that makes you understand what I'm talking about here. But now instead of considering 100 separate trials out of the million or even a million trials that you did for one length L, now we're imagining as if there's a million labs, and all of these labs are just as awesome as your lab is. So they can do just as good a results as you do. And what you'd really like to know is what would 68.1% of those labs or what would 68.1% of those L values that those labs chose. In other words, what range of values do you expect the length to fall in as a result of looking at those million labs? And in doing that, all we have to do is do a standard error calculation instead of a standard deviation. And it turns out that the difference between a standard deviation and a standard error is you take the standard deviation, which Excel can calculate for you, your scientific calculator can calculate for you, and you just take it and divide it by the square root of the number of trials. That gives you the standard error. And what the standard error represents is basically if you took a million labs and a million of those labs did, however many measurements they need to actually determine the length, what you would want to know is what is their best values of length. And that's what the standard error allows us to figure out, because it would tell us basically out of those million labs, 681,000 of them would come back with a value between the mean minus the standard error to the mean plus the standard error. 95.4% would be two standard errors from the mean, and 99.8% would be three standard deviations from the mean. So that is usually what scientists use when they're talking about error in results. They're talking about the standard error. So if you see, for instance, a measurement listed as 1.369 plus or minus zero point zero zero 0.002 meters, that 0.002 is usually a result of a calculation of standard error. Okay. Now that's for stuff that you're actually just making direct measurements of and then doing some statistics to figure out what the best result is. Now, when you actually have that length and you have that width and you have that height, for instance, for a rectangular object, each of those have their own little errors, plus or minus zero point zero zero 0.002 or plus or minus zero point zero zero 0.004 or something like that. Each of those are going to have their own little standard errors. Now, what happens when you take those three numbers, length times width times height, and multiply them to get a volume? And what value do you use? Hopefully, it's obvious that you should use the mean, obviously, for the best value of the length, the best value of the width, the best value of the height. So you take the mean of the length times the mean of the width times the mean of the height, and that'll give you the best estimate of the volume. But now that you have that, like in this case, I calculated the best height on average was 56.39333 centimeters. Okay. That's from the data I gave you. So I didn't cut off any decimal places. I showed them all because that's what your calculator is going to spit out at you. You know that you measured all these to 4 sig figs. So you might think, well, according to sig fig rules, then this should be called 56.39 centimeters. But is that right? Is that really a robust way of doing such a calculation? It turns out, nah, not so much. Okay. What's supposed to happen now is you take the standard deviation of these four numbers. Now, in this case, it's really four trials, so it's not that good of an experiment, but it gives you the idea of what's going on here. So you take the mean, and that's going to be what you represent as 56.39333 centimeters. But then you take the standard deviation, and then you take that standard deviation and divide it by the square root of the number of trials, which in this case, actually, I said four earlier. I think it's actually five. No, it looks like one, two, three, four, five. Oh, six of them. Sorry about that. So you take the standard deviation and you divide it by the square root of six, and that'll give you the standard error. And according to my calculations, my standard deviation was 0.0121 centimeters. And later you'll find out that my standard error was 0.00494 centimeters. Okay. So you can see that the standard error is a slightly smaller value than the standard deviation. And that's, by design. But the main thing is that's what you would now use to actually round it. How do we do it? Well, it's this. First, if I say that there's an error of like 4 in the third decimal place, by the way, that's tenths, hundredths, thousandths. So that standard error tells me there's an error of 4, in the thousandths place. Then if there's really an error of 4 in the thousandths place, do I have any idea what the 10,000th place is? No, I do not. Absolutely. If there's an uncertainty of 4, meaning that third decimal place could be a 4, a 5, a 6, a 7, or an 8, or it could be down to 0. That's what plus or minus 0.004 means. Then I have no idea what the next digit is. So it's really not very sensible to use more than one significant figure on a standard error. But there is a time where people often do, and I express that here. That's when that first digit, instead of it being 494, that first digit being the 4 to the left of the 9, if that first digit were a 1, then a lot of people will choose to use two digits. And the reason being is if that second digit, in other words, instead of the 4 and the 9, we had a 1 and a 4, that 4 is literally 40% of the 1. If that digit was instead of a 4 and a 9, a 1 and a 5, then that 5 is literally 50% of the 1. Okay, so a lot of times when the two digits are 0.0014 or 0.0015 or 0.0016, uh, a lot of times people will take the time to write that error as 0.0014 or 0.0015 or 0.0016. That's okay. I'm never going to take off in my classes, in my labs. I'm never going to take off for you not doing that or for you doing that. But in general, all you really have to do is round your standard error to one sig fig, and that sig fig, since we can't know the digits to the right of that, then we shouldn't know the digits to the right of that in the mean either. So that's where we choose to round off the mean. So for instance, in this case, the standard error was 0.00494, which we would call 0.005, because clearly that 9 is telling us that this digit should be a 5. So 0.005 is the uncertainty, and that means that we should round our mean to the thousandths place, not to the hundredths place, like the significant digit rule said. So specifically, we would report this number as 56.393 plus or minus 0.005 centimeters. So that's the way you do it. Here's the rules. It says rule one, when several measurements are made of a single quantity, the average or weighted average is the best estimate of the value. As I told you, the weighted average would be the gold standard, but you have to have a different uncertainty for each trial for you to make sense of using a weighted average, and we're never going to do that in our labs. Okay. But again, the best value is the mean. Okay. Rule two, the larger of the instrumental slash measurement error of the or the standard error are to be used as the uncertainty of the measurement. So for instance, I already talked to you about a meter stick having at best an uncertainty of zero point zero 0.01 centimeters, meaning plus or minus 0.01 centimeters. That's the instrumental uncertainty, and you cannot do any kind of statistics to make that better. So if you're measuring with a meter stick and you ever calculate a standard error that's less than zero point zero 0.01, then you just wasted. I shouldn't say wasted, because you actually have to do it to be a good experimentalist, but you basically did a calculation that ultimately led to a result that you couldn't use. So if you got 0.008, okay, then you can't call that 0.008. You have to call it zero point zero 0.01 at best, okay, because that's the best that a meter stick could do. However, if you're using vernier calipers, then if you got a standard deviation of 0.008, or excuse me, a standard error of 0.008, then you could use the 0.008, because that is consistent with the uncertainty, the best case scenario of the uncertainty of a vernier caliper. Really, a vernier caliper probably has an uncertainty at least of 0.001, but a lot of times I don't think I've ever seen anybody use anything other than 0.002 for a vernier caliper. But I guess that varies from person to person. So, anyways, that's rule two. The larger of the instrumental slash measurement error or the standard error is what you have to use for the error of a direct measurement. Okay. I will tell you also that well, I'll just leave it at that for right now. Now, rule three, the uncertainty of a given measurement should almost always be recorded with only one significant figure, because if we don't know the leftmost leading digit with high uncertainty, we definitely don't know the digits to its right. That's the thing, same thing I was explaining to you a second ago. If the standard error is 0.00494, having an error of 4 in the third decimal place means the error of 9 in the fifth decimal places, or in the fourth decimal place, is almost meaningless. Why do you why would you even list it? So that's all that's saying. It says the uncertainty of a given measurement should almost always be recorded with only one significant figure, because if we don't know the leftmost leading digit with high certainty, we definitely do not know what the digits to its right are. The only time you may wish to use two sig figs is when the leading digit is 1 and the second digit is a 4 or 5, or maybe larger. I tend to think once you start getting around to 7 or whatever, you should just probably round it up to 0.002 or whatever. Uh, But in our labs, I will never take off for using this practice nor for not using the practice. Rule 4, your measurement's best estimate should be rounded off at the same digit as the last digit of your uncertainty. For instance, if your uncertainty is 2 in the thousandth digit, meaning the third decimal place, then your mean calculated value should be rounded to the third decimal place. Where did that go? Oh, the whole sentence disappeared. Oh well. Must have erased it before I saved it. I'll fix that, but it should be rounded to the thousandths too, is what I'm supposed to say here. Rule 5: when using certain measurements to compute something else, you must use the best estimate for the values of the measurements, and error propagation formulas should be used to determine the uncertainty in the calculated quantity and to learn where to round off the calculated quantity. So, for instance, that's where I was saying if you had a length, a width, and a height, each of those have their own uncertainties, which may be instrumental uncertainties or it may be standard errors. Doesn't matter. The main thing is you have to take the larger of the two for each. And then when you have the errors with each L and W and H, what you're supposed to do if you calculate volume equals length times width times height is you take the mean value for the length times the mean value for the width times the mean value for the height, and that gives you sort of like the H was 59.39333 or whatever centimeters. That gives you a multitude of digits to use, but you don't necessarily know which ones are helpful at this point. Then you apply the propagation of error formula, which we're going to teach you in a second, and that'll give you something just like the standard error so that you can use it to round it probably to one sig fig and then round the result of your calculation, length times width times height, to that same decimal place. So here's the way you calculate standard deviation. You have to take h minus the mean and square it. If you actually tried to do the deviation without square, you'd end up getting 0. So it turns out it's best to use the deviation squared. And by doing that, you don't end up getting that 0 and you don't, well, the main thing is you get a better value. So we're sort of taking the average of the difference between the mean and the individual trial. But when you try to actually calculate the difference between the mean and the actual trial, that averages out to 0 because there's just as many negatives as there are positives. But if you square it, then that gets rid of the negatives and therefore you get a better value. Well, it turns out you would like to do that, but you also want it to have the same units as the value you're measuring. So, for instance, if you're measuring length and centimeters, you would like the standard deviation to come out in centimeters. So, in order to do a square, you're going to have to take a square root to get back to the centimeters. Otherwise, you'd be using centimeters squared. So you do that, and then this way you're sort of thinking about, okay, so it's the average of the squares of the deviations. So you'd think you'd go ahead and take that sum of the differences squared and then divide it by n. But it turns out that a lot of times we don't use sample sizes that are big enough for these statistics to apply. So they advise us to use n minus 1 to correct for that. So you can just imagine it that it's going to be n minus 1 and that's it. Again, your standard deviation or your standard deviation formula in Excel or in your scientific calculator does know how to do this calculation. And to verify it, you're going to take this table down here later on. You're going to take this table down here and complete it. In other words, you're going to take those same 6 values that I gave you and you're going to calculate h minus h bar for each of them. Notice some are positive, some are negative. Then you're going to take and square each of them, and that's going to give you these. And then you're going to take that and sum them all up, and that'll give you basically this summation from I equals 1 to n of h minus h bar squared. That's the numerator under that radical is this sum right here. Now you're going to take that and divide it by n minus 1, n being 6 is going to be 5. So you divide this by 5 and take the square root of it, and you get this number out, 0.0014667. And that should be your standard deviation. Now, if you want the standard error, all you have to do is take the standard deviation and divide it by the square root of the number of trials, which is 6. So now if you divided this by 6, you should get that number. So this table allows you to verify that your formulas or your Excel and your calculator are using the same formula as we are, and therefore give that a try. So you're supposed to use that. It tells you how to use the table here. There's the standard error. You can see the differences. You can almost see it's like they're doing an average of an average, or they're doing a standard deviation of a standard deviation. And that's why they call it the standard deviation of the mean. But ultimately, it's given the symbol sigma. And if you're measuring a quantity called h, then you call it sigma sub h, and that's your standard error or your standard deviation of the mean. And it's the standard deviation divided by the square root of n. There's another quantity we use specifically for the propagation of error formulas, and it's called fractional error. And it's that uncertainty, which could be a propagated uncertainty like we get from error propagation formulas, or it could be a standard deviation, or it could be an instrumental error. It doesn't matter. It's just you're using the right one. So whatever error it is in that particular quantity, you take that and divide it by its best estimate. That's called the fractional error. The symbol we use for it, oddly enough, is sigma h over h. And the formula for calculating it is sigma h over h bar. So it's a formula and a symbol, but notice the difference is you actually have to plug in a specific value of h, and this formula tells you that specific value is the mean. Obviously, again, the gold standard is the weighted mean or the weighted average, so you would use that if that was available to you, but again, we're not going to use that in our lab at all. All right, here's the propagation of error formulas. Specifically, if f of x equals some constant times x, let's call it cx, it turns out that the standard error is equal to the value of the absolute value of c times the uncertainty in x. This actually comes from this formula right here. So this is the calculus formulas that we're actually using, but here I've given it to you as just a formula you're going to apply. So for instance, if you're, let's say, converting a unit, you obviously have measured a value x, and let's say it's in centimeters and you want to convert it to meters, then f of x could be just the multiplication of x, which is in centimeters, by 1 meter divided by 100 centimeters. So the C should be 1 meter divided by 100 centimeters. That's an example of error propagation. So you want to know, well, what is it? And hopefully this one makes perfect sense. It's just that 1 over 100 times the uncertainty in the centimeter mark. So it's literally just converting the uncertainty, which was in centimeters, to uncertainty in meters. If you add two numbers, it turns out that the sum of the squares of the uncertainty of the two numbers is the sum of the squares square rooted is the uncertainty in the sum. If you do a difference, it's the same formula. If you do multiplication or division in really any order, it's the same thing as these formulas up here, except the formulas turn out to be in terms of the fractional errors instead of the standard errors. So that's something important, and that's why we introduced the fractional error. So these are the formulas you would use for x times y, or for x over y, or for x times y times z. There's obviously supposed to be a z right here. That's another error that's not in it. I'll type it in now. Okay, so I got to fix that, and I also got to fix, I'm going to write up here where I left off part of that sentence. Actually, I erased it. I didn't know I fixed it just before class. I'm just putting a bunch of stuff there, so I'll obviously see it next time and realize it's crap. All right. So these are some formulas you'll use day in and day out, and I need you as a calculus-based physics class to be able to come up with these formulas too, at least for the simple cases. So the general formula we use is if you have a function or you're using a formula to calculate a value using uncertain values that have a physical uncertainty, then that's a single variable function. And it turns out the uncertainty that comes out is equal to the absolute value of the derivative of f with respect to x times the uncertainty in x. So again, I gave you an example of converting units, but you could also say, what if you take an angle theta and that has an uncertainty plus or minus sigma theta, and then you take the sine of it? What are you going to do? Well, that's a single variable function. So the uncertainty in sine of theta is equal to the cosine of theta times the uncertainty in the theta. And obviously, you're going to have to make sure you use radians in certain cases and stuff like that. But that's an example. Additionally, if you have many, many variables, I happen to show you in this case three. If you had any number of them, you're going to do this over and over again. So it turns out for a function f of x, y, and z, meaning a function of three variables x, y, and z, then the uncertainty in using that formula, the uncertainty that you get out from using that function is the uncertainty in f. And the uncertainty in f is given by the sum of the squares of the square root of the sum of the squares of, you take the partial derivative of f with respect to x, you square that, you multiply it by the uncertainty in x squared. You take the partial derivative of f with respect to y, you square that and multiply it by the square of the uncertainty in y, and you take the partial derivative of f with respect to z, you square that and multiply it by the square of the uncertainty in z. You add those three quantities together and take the square root, and that spits out the uncertainty. So I go through working again the same example above here so that you can see how it's actually implemented. And it turns out that sometimes it's better to calculate the standard, or excuse me, the fractional error instead of the standard errors. Notice this is just a standard error here, whereas this is the fractional error. And the reason why, for instance, when I did uh, f equals x times y times z, then the partial derivative of f of x, y, z, which equals x times y times z, the partial of that with respect to x is what you get by just pretending like y and z are constants. So x, y, z, where y and z are constants, is like 2 times 3 times x. The derivative of 2 times 3 times x with respect to x is just 2 times 3. Only you don't put in the 2 times 3, you put in the y times z. So you can see right here, I got the y times z. Similarly, the partial derivative of f with respect to y is pretending like the x is a 2 and the z is a 3 and the y is the variable. So 2 times 3 times y, that would just be 2 times 3, which gives me x times z, and so on and so forth. It turns out, though, when you do that calculation, if you decide to divide by the formula again, which is x times y times z, you can actually square that to pull it inside the radical, and then it can make beautiful cancellations, and you get this really nice, clean formula. The standard error in v is equal, or excuse me, the fractional error in v is equal to the sum of the squares of the fractional error in x, fractional error in y, fractional error in z. That was why these formulas worked out so nicely for the same, and give you the same formula for x times y, for x over y, for x times y times z. All of those all came out to these nice simple formulas. Okay, so that's how I use it. I do some examples where I actually show you the derivatives, and your job is to actually use that you learn to show that the error for f of x y equals x plus y is equal to this. Then you're going to do it for x minus y has an error equal to this. Y minus x has an error equal to this. X times y times z has an error equal to that, and so on and so forth. These are just x and y, so I don't seem to have any errors on that. And you're going to fill out this table as I explained to you up there above. And I think that's it. Let's see, example 8 or number 8, learn to use your calculator statistics package. Yeah, you definitely need to do that. 9, use the following data for the dimensions of a rectangular solid. Okay. To calculate the best estimate for the volume of the solid, do not do a weighted average, and the uncertainty in the volume. Finally, properly report the experimental value of the volume and its uncertainty. So that's the other lab you have to do. It me explaining it takes way more time than it takes for you to do it. The only thing that might give you a little problem, because students sometimes just get scared by seeing these crazy partial derivative stuff. So seeing these crazy partial derivatives, that might trip you up a little bit, but just ask me. Ask me in lecture, ask me online or whatever. Send me a text message. I'll be glad to help you walk through that. But really, the rule is just pretend like all the other variables, when you're calculating a partial derivative, pretend like all the other variables are constants, and then make sure you leave them as those other variables, but treat them as if they're a constant. So if you had, for instance, x plus y, and you want to take the derivative of that function x plus y with respect to x, then that's like x plus 4. And the derivative of x plus 4 with respect to x is just 1. So the partial derivative of x plus y with respect to x is just 1. The partial derivative of x plus y with respect to y is also just 1. The partial derivative of, or let's say, if your function's f of x equals, or f of xy equals 2x plus y, then the partial derivative of f with respect to x is 2. If you take the partial derivative of f equals 2x plus y with respect to y, it's just 1. So hopefully that'll help you. But that's it. That's the entirety of this. I'm going to go ahead and fix this right after I get offline, fix these things and re-upload it. So don't upload it right now. It should be able to be uploaded by 2 p.m. Okay. Let's stop sharing. And now I've finished everything. No one came for office hours, so I'm assuming that's okay. Feel free to contact me. Remember, if you're in my online class, which obviously you are, we do have a face-to-face test that's due this week. Technically, I think I gave you till Monday, so you have this week plus Monday to get that done. That has to be proctored. You can use the testing centers at any of our campuses. They're free, but you have to contact them and find out the details. You also had an online test that was due last week that I've now pushed back an extra day. Actually, it was supposed to be due by 11:59 p.m. Yesterday for my Tuesday, Thursday classes, and I pushed it back now to be done by Wednesday at 11:59 p.m. So you still have that for that online test that needs to be done. And then you have the face-to-face test that has to be done sometimes this week or possibly Monday by 11:59 p.m. And that's it. I hope this helped. Let me know if you have any questions and have a good day.